Davis, and I work in the area of soil and water chemistry. And I have been working here on research projects at the field station for 20 years now. It was my very first research project looking at nutrient cycling here in the oak woodlands. So my charge today is to provide a little bit of an overview for more of the detailed material that Ken and Toby will be presenting here in a little bit. So if you have questions as we go along here, I'm happy to answer those. So the oak woodland community is a very important community with respect to water quality. It exists at the urban wildland agricultural interface, so as you drove up today, every day there's more and more houses in this part of the world, and with all the fire problems, we have to manage the fuels, and that often involves grazing and or prescribed fire, as was just mentioned. So these are things that can alter the water quality. Also, 80% of the reservoirs here in California are located within this oak woodland community. Therefore, things that are happening just in the immediate vicinity of these reservoirs in the oak woodlands can have some major impacts on the water quality within these reservoirs. So a very important area in which to focus studies on water quality. So water pollution is a human-induced alteration of the physical, chemical, or biological integrity of the water. It can range from putting nutrients into the water, removing riparian zone vegetation, which affects the temperature, sedimentation of the salmon spawning grounds, and pathogens such as E. coli and other critters, which are important. From a water contaminant perspective, we need to understand where these pollutants are coming from. We have point source pollution, which comes from an identifiable source, such as a sewer pipe discharging into a water body. Rangelands are part of the non-point source pollution, which is originating from a diffuse area. You can't pinpoint directly where it's coming from. So we typically break our pollutants into point source and non-point source. But something we often fail to recognize is that there are a lot of natural sources of pollutants in the environment which have nothing to do with human influences. And this is especially true for several constituents here in the oak woodlands, such as sediments and nutrients, which I'll touch on here briefly, and then turn it over to the rest of the team here to describe this in detail. So natural sources cannot be overlooked. Okay, so with respect to regulation, every water body is assigned a designated use, such as drinking water or recreation, and water quality standards are developed then to meet these objectives. If the water quality standards are not met, we say that this water body is impaired, and we have quite a system here in California for dealing with that. The Clean Water Act, 1972, started looking primarily at point source water pollution, and then with time, once technology was able to solve a lot of these point sources, now we are very focused on the non-point source pollution, such as rangelands, agriculture, urban runoff type things. And the goal here is to maintain the integrity of our nation's water, but more easily stated is all water should be safe for swimming, fishing, and drinking water. So that's sort of the goal of water regulation across the nation. So in California, if water impairments occur on a given water body, they are put on this list that's called the 303D list. And in California, as of 2006, there was approximately 779 water bodies that didn't meet these water quality standards. They have been put on the list, and now action is being taken to alleviate these problems and clean them up so that impairment does not occur. Within these 779 listed water bodies, there was 2,237 impairments, which means there's often multiple problems with a given water body. There's 176 different types of pollutants which are contributing here, all the way from garbage in waterways in LA to E. coli and mercury. DDT, legacy issues are still a problem here. And they affect huge river miles and lake miles here in California. So it's quite a task here to deal with cleaning up these water bodies. If we look at the top 10 impairments here that occurred based on the 2006 data, which is on a website here from the State Water Resources Control Board, this is the number of impairments. Pesticides is the number one. There was about 450 water bodies that had pesticides that were deemed a problem. Metals, often coming from abandoned mines. Pathogens, such as E. coli, Cryptosporidium parvum. Nutrients, different types of organics, sediments, toxicity, and salinity. So from a statewide perspective, these are where the problems are found. So with this data in mind, the Rangeland Water Management Team, with Ken Tate in charge here, did a statewide survey. We wanted to figure out on rangelands what are the major problems that we should be concerned with. So we got several collaborators, probably some of you in the room here, who on various, every 2 weeks or during rain events, sent us samples to the lab, and we looked at these 24 locations, snow-dominated systems, rain-dominated systems throughout the state in water years 2000, 2001 to look at what the major problems might be on California rangelands. And here's a little bit of data. Nutrient concentrations for total nitrogen, nitrate, ammonium, total phosphorus, and phosphate. And looking at this in terms of a distribution here, with the median value being the 50th percentile and 25th and 25th percentile of the data falling within the box, and the 10 and 90th falling within the whisker there. So if you look at this data and put it in the perspective of water quality impairments, nutrients are generally not a big problem on California rangelands. Nitrogen concentrations here are almost nil. Ammonium is nil. A little bit of total phosphorus, but the phosphate, which is most important in driving eutrophication, is really non-detectable. So the bottom line is nutrients is not a huge problem here in the 24 sort of characteristic sites that we looked at. Pathogens, this becomes a little bit more of an issue here, and we see that here's the concentrations of E. coli, the dark blue, fecal coliform, the lighter blue here, and the red dashed line here is the E. coli standard of 128 units. So for many of our rain-dominated systems here, and the E. coli is for E. coli is the dashed line here, the regulation, you'll see that many of the sites do exceed the regulatory limit for that. Rain and snow-dominated sites, less, and by the time we went to a snow-dominated site, there was very few exceedances of this E. coli issue. So the bottom line here is that, yes, E. coli pathogens probably turns out to be one of the more difficult tasks on the rangelands, and in several instances here, we do see some exceedances above the regulatory limit. So, in summary, when we come to looking at rangelands, the primary things of interest, nutrients, sediments, and pathogens, it turns out pathogens here, at least in California, is probably the one that we need to focus most of our attention on. Well, if that isn't enough, new ideas are emerging here that we need to tackle. And one of the other constituents now, which is being talked a lot about in terms of drinking water, is dissolved organic carbon. And this color you see here, it looks like tea. That is material that's been leached out of natural vegetation, out of oak leaves, out of the annual grasses themselves. And when this ends up going into a drinking water system that gets chlorinated, the chlorine interacts with that dissolved organic carbon and forms what we call disinfectant byproducts, which are carcinogenic. And the one that I show here as an example is chloroform. So when you add chlorine in the water treatment process, you can form these potential carcinogens. So this has raised a lot of concern in oak woodlands, and I'll show you why that is here in a minute. But again, natural sources. It's the trees, it's the grass that's contributing this DOC. It's not coming from anything that humans are applying to the landscape. And in fact, if we graze this landscape, if we burn this landscape, we might remove this vegetation and actually decrease the amount of dissolved organic carbon coming from these watersheds. And Dr. Ogene will talk a little bit about that in a little bit here. So just in terms here, so disinfectant byproducts that are formed during chlorination, you might hear the terms trihalomethanes is one category that's regulated. The other is the haloacetic acids, and you'll see these various structures here that are oftentimes carcinogenic and of great concern for the water treatment community. Okay, so is it a problem here in California oak woodlands? Well, let's take a quick look at that here. And the first thing I want to point out is that this dissolved organic carbon changes as it moves downstream. The sun causes photooxidation, photodegradation. The UV light oxidizes the dissolved organic matter and destroys it. We also have the microbes getting a meal out of it, biodegradation. They're eating it as a food source. And then also within the stream environment, in certain environments, we have algae that are actually producing more DOC. So just because it came off of a field doesn't mean it's going to get down to that drinking water source where chlorination occurs. So as an example of that, I just want to use data we have here. Here we are located up on the Yuba River at the field station. And we also have long-term monitoring data from just above the Feather River at the end here of the Yuba River looking at DOC. So what I want to show here is a concept that's termed assimilative capacity. And that means the capacity of a water body to receive a pollutant without harmful effects or damage to aquatic life or the humans that utilize this water. So there's lots of processes occurring within the stream during transport that alter these pollutants. They can end up removing the pollutants altogether, for example. And let's see what happens here in our trip down the river. So up here near the field station, this is the dissolved organic carbon in the stream water from October to September, so one full year. We often see a big pulse of DOC coming out in the fall and the early winter months. And that's because we got all these fresh leaves and all this dissolved organic carbon leaching out of the foliage and grasses, and it hits the river with high concentrations coming out of the headwater streams here. As this gets flushed out of the system, then we see much lower concentrations, but still concentrations here that generally fall right around 3 parts per million throughout the summer months. And the reason I drew that red line there, that is a guideline. They want to try to keep DOC concentrations less than 3 milligrams per liter at the the drinking water treatment site to be able to prevent high levels of the disinfectant byproducts. So if you look here, right at the field station, you would say, wow, we might have a problem with dissolved organic carbon in the water. But if we go down to Yuba City now, a couple days away for the water, now I have the 3 part per million line right at the top of the graph, and from 1999 to 2003, we see concentrations at Yuba City are more around 1 to 2. So in transport from the field station down to Yuba City, we've had dilution from some water coming from upstream. We've also had photo and biodegradation destroying DOC. So if you regulate at the end of the cow or at the headwaters here, you'll probably identify a problem, but if you go down to more lightly where the drinking water is going to be chlorinated, the problem does not exist. Okay. Same thing can happen with nutrients. Very interesting nutrient cycling here in California because of the rainfall pattern, this Mediterranean climate, dry during the summer, wet during the winter. So here is data on nitrate nitrogen. So this can cause eutrophication, algae growth downstream. And this is 3 years of data here, starting with January at each of the vertical lines here. So early in January, we often see spikes in nitrate, and then throughout the season, growing into the summer months, the concentrations go down, only again to spike again during the February period every year. So what is contributing to this pattern here in nutrient leaching from the watersheds? Well, it has to do with the vegetation again. So during this time of year right now, the oak trees have dropped their foliage, the annual grasses are basically dead here, and a large part of the nutrient pool contained in this organic matter has leached into the soil, and once we wet up the soil in the fall, we get an explosion of microbial activity which produces the nitrate. If there's not enough rain to leach it out of the soil, it accumulates in the soil, And then come December and January, when we get the big rainfall events, this nitrate, along with that DOC, is liberated and goes into the stream. Come late February, March, April, then the annual grasses are sucking up a lot of nutrients. The trees are also taking up a lot of nutrients, and the concentrations in the soil are depleted, and as a result, in the stream water, nitrogen is lower. So you might look like we have a problem here in the fall, in the early winter, but for most of the year, nitrate concentrations are very low. If we go back to our example at the Yuba River, from the previous slide, I showed maximum values of about 5 milligrams per liter of nitrate nitrogen leaving the headwater catchments here. But by the time we travel downstream to Yuba City, concentrations are 0.1. They have been attenuated over an order of magnitude by different processes occurring in the stream. Some is the dilution, but some is the loss of nitrogen to processes like denitrification and also plant uptake along the way. So, where you monitor makes a big difference in whether you perceive you have a problem or not. And as another example of this, I just want to show some data that I've got from below a sewage treatment plant. And we collected data 2 miles down from the sewage treatment plant and also 5 miles down from the sewage treatment plant. And these are parts per million here of nitrate, nitrogen, or phosphorus. And at the 2 mile mark for nitrate, we had 15 parts per million of nitrate nitrogen. But go downstream 3 more miles to the 5 mile mark, and that nitrate was almost removed completely. So the assimilative capacity of the stream was able to take care of that nitrogen. And a similar pattern here is found for phosphate. High concentrations at 2 miles, but go a little further down, and much of it has been removed. So assimilative capacity. Sediments can be a problem, especially under certain pasture management regimes. And work by Ken Tate, Dave Lewis, and others in the Coast Range found that 99% of the sediment that was being generated was due to legacy effects or historical management effects, such as this landslide here that was probably created because of tree removal ultimately. But really only about 1% of the sediment that was being generated from the rangelands was due to current management activities. So one needs to start separating legacy issues from current management issues when looking at things such as sediment. And it is a natural source, and the reason we've got valleys here is because of natural geologic erosion that's occurred over time. Another interesting study, at least I thought it was an interesting study we did, was a controlled release flood on the Mokelumne River. They actually wanted to flush out the sediments to improve the salmon habitat there. So we set up samplers, auto samplers downstream, and I just show a little bit of the data here, 0.7 miles downstream from the dam and 16 kilometers downstream from the dam. And what they did was they ramped up the lighter line here is the hydrograph, so how much water was coming down the river. So they ramped up every day. They increased the water flow, simulating a natural flood event. And then once we reached the peak, they ramped it down over the succeeding period of time. And what we found was this water was only coming from the dam and the reservoir. There was no connection to the landscape and management activities here. It was only coming from the river sediment. Every time they ramped it up, we saw spikes here for total suspended solids or sediments. And each time we ramped it up, the peak got a little bit higher. And as we went downstream, things picked up even more. So the source of this sediment was not from management activities. It was from the stream channel itself. And not only did total suspended solids increase, but E. coli shot up way above the standards. Nitrogen shot up way above what we would normally expect to find. So just storage of pollutants within the stream channel can cause some of these apparent problems with water quality. So it doesn't have to be associated with the landscape. There's lots of pollutants within the channel itself. And that needs to be considered during big storm events. So now just a few comments on water quality monitoring, which is becoming sort of a big thing now in the ag community. With the Irrigated Lands Waiver Program, coalition groups, farmers are being asked to do water sampling once per month. And does this make sense from a scientific perspective. That's something that we've been looking at here over the years. So first I start with looking at from year to year variability. And this here is the Shubert Watershed, which you'll see today. And Mike Singer, a colleague of ours, started monitoring water quality here in 1981, and this record continues till today. So we got about a 27-year record on what's happened with nitrate leaching from this watershed. And this is the amount of nitrate in kilograms per hectare per year. Doesn't matter what the units are, but what I really want to show you here is that from year to year, we can see huge changes in the amount of nitrate coming from a river. And this is due in part, number one, to how much rainfall occurs in a given year, but also to the distribution of rainfall. Remember from the earlier slide, rainfall early in the season flushes lots of nitrogen. Rainfall late in the season doesn't flush much nitrogen from the soil. So the amount and distribution of rainfall affects how much nitrogen is lost from a stream. So this suggests that you need multiple year record before you can determine whether there's a problem for things like nitrate. I showed you this data here. This was the changes over time on about a 2-week time step here. So when you go out and sample, depends on the seasonality of the pollutant. And if you went out once a month, you would probably be able to capture this sort of record here. Okay? The one record that's hard to capture, though, is during storm events themselves. Here I show nitrate concentrations from 0 to 10 parts per million over time during 2 storm events. The first storm event of the year and one that occurred about 2 weeks later. So during this first storm event, the hydrograph came up, the stream came up, and it came down. And what happened with nitrate is it started off pretty low, but that first flushing of the soil, as I showed previously, released a huge amount of nitrate into the stream water. And then as the stream water went down, the nitrate concentrations also decreased. And Professor O'Gene here will tell us more about why this is a little bit later. But then 2 weeks later, when we had another even bigger storm event, concentrations started off kind of high where they left off here, and then concentrations decreased during the heart of the peak of the storm event. And this is because there was so much water coming in that we actually diluted the amount of nitrate that was coming out of the soil. So during storm events, you can get very different measurements whether you go out during the peak of the storm or a couple days later. And I know from a water quality perspective, I'd rather be sitting at home and watching football during the heart of the storm and go out a little bit later on a sunny day to collect, and that'll make quite a difference here in what values you get. A study that Dr. O'Gene and a graduate student have conducted was looking at agricultural tailwaters from a site down in the San Joaquin River. They collected water every 6 hours for the entire irrigation season. That amounts to like 500 samples. And the next year they went back and they collected daily composite samples, so 1 sample a day, but each sample consisted of 4 subsamples taken throughout the day. So they got this long-term record here for the irrigation season. Concentrations varied from 0 up to about 70 parts per million of total nitrogen. So huge variability from day to day, from hour to hour, actually. And in getting a record like this, you can start to ask, well, how many samples do I need to take to get an accurate representation of what the water quality is coming from those fields? So the data was statistically analyzed. The mean value was 8.4 for the data, and 95% confidence intervals were put around this mean value. So if you wanted to be within 20% of this mean value with a 95% confidence interval, you would have to collect on the order of 80 samples per year to meet those criteria, which obviously we can't afford to do on some of these ag lands. If you want to lower your standards a little bit and say, hey, I want to be within 50% of the mean with a 95% confidence interval, well then we probably only need about 15 samples per year. So from a regulatory perspective, this is a real challenge. How do you design a monitoring program that is statistically valid for a given region? Taking 1 sample a month in many cases is going to be totally meaningless. So a challenge there, and there's no easy answer to this question that I know of. Okay, we're getting to the end here. The other thing is what time of day you take a sample makes a huge difference too. Now in this data here, I'm just showing from noon to midnight, so each of these is a 24-hour cycle in dissolved oxygen concentrations in the San Joaquin River. So if I go out here at the end of the day when the algae has been producing oxygen all day by photosynthesis, I get concentrations upward of 18 parts per million. If I come just before sunset, 6 a.m. in the morning, when there's been no photosynthesis to produce oxygen, but the bacteria and all the living critters have been consuming oxygen all night, just like we are here through the respiration process, then the concentrations drop to less than 7 parts per million. So what time of the day you go out makes a huge difference here. Not only for dissolved oxygen, but there's a lot of constituents that change from morning till night. And lastly here, in designing water quality standards, and this is a question that Ken had brought to him here recently, you really need to think about these water quality standards. What we use in the San Joaquin River does not necessarily make much sense for 5,000 feet elevation in the Yuba River. And the reason is that things like dissolved oxygen concentrations here, they vary as a function of temperature, and they vary as a function of elevation. So let's pick the 20-degree line here. At sea level, basically the saturated concentration of oxygen, the most oxygen you can get there in equilibrium is 9 parts per million. So that's the max you could get there. But if we were up here at 6,000 feet elevation, the maximum level you could get is on the order of 7 parts per million. So a standard of 7 parts per million, which might work in the San Joaquin River, which is near sea level, doesn't give you any degrees of freedom here at 6,000 feet elevation, because the maximum value you could possibly have is only 7. If that's the standard, you're probably not going to be able to achieve that throughout the year. Well, that is what I've got with respect to sort of the background. And I just, in transitioning here and segueing to the next talks, I wanted to just give you a brief history of the 20 plus years of research and extension that's been going on here as part of these studies. This here is the Shubert Watershed. It's about 250 acre watershed. 27-year record, continuous record of water quality here. Begun by Mike Singer, carried on today by Ken Tate and company. So lots can be said and done based on this long-term record. So here's a picture of the gauging station here at the bottom of the Shubert Watershed, where the water volume and the water chemistry is recorded. Studies have gone on. We have 4 paired watersheds here, the Shubert plus 3 more, where we've looked at the effects of grazing and how much the grazing impacts, all the way from no grazing to having only 500 pounds per acre of residual dry matter. And I think Toby's going to present some of that later on. So look at the effects of grazing intensity, looked at the effects of fire on water quality. So things change a lot when you burn the landscape. One of my favorite discussion topics is the individual oak trees create islands of soil fertility beneath their canopy. You really can't see it coming up here today, but if you come back in, say, February and March, you'll see much more luxuriant grass growth beneath that oak tree. Because those oak trees, through various processes, increase the amount of nutrients and carbon stored here by 50% relative to the adjacent grasslands. Okay, and be happy to talk to you more about this later if you desire to do so. We've also looked at the effects of what happens to these islands of soil fertility if you remove the tree. And believe it or not, after about 20 years, that whole island of soil fertility disappears. And that's exactly what they found with the early rangeland work here, where they showed that you've got a big increase in forage production when you remove the tree, but after 15, 20 years, there was no advantage beneath the tree removal area. Professor Eugene is going to talk about the effects of hydrologic flow path. How the water flows through the watershed makes a big difference on the water quality. And I won't steal any more of the thunder there, other than to show the trench plot here that was used for that. Ken Tate has done lots of work with irrigated pastures here to look at different effects, including here's the bottom of the irrigated runoff plots here, collecting the water quality to see how you can maximize nutrient and pollutant retention within these runoff plots. And here are some RDM plots that Ken is talking about, and I think you'll maybe get a chance to see some of these today. And finally, we'll show a little bit more about this, but this is a small little wetland that exists just about a quarter of a mile down the road here. And by taking these waters coming off the irrigated pasture and simply flowing it through this wetland, it takes about 1 hour to go from the top to the bottom of the wetland, you can remove from 50 to 80% of the pollutants of concern. So wetlands might be an option here for enhancing water quality. And then finally, there's been a lot of extension that goes on as part of the studies, as you are all part of today. So with that, I'm going to turn it over to Ken Tate. Ken Tate is with the Department of Plant Sciences and has been instrumental in all of the research you have seen here.
We don't want to let Randy off. Well, let's thank Randy first.